Hi everybody. In this video, we're going to look at solving geometry problems with 3D vectors. We'll work through 3 questions, and if you want to work along with me, you can download this PDF from my website. I'll leave a link in the description below. So in example 1, we've been given O to A is vector A, and O to B is vector B. We're told that M is the midpoint of O to B, so we'll sketch this about here. And N is the midpoint of A to B, so we'll sketch that about here as well. We need to find O to M and O to N in terms of A and B. So we'll begin with O to M. You can see that this is 1/2 of a vector O to B. And we know that O to B is just B. So O to M will be 1/2 of B. O to N, this will be O to B plus B to N. And B to N is the same as 1/2 of B to A. And B to A is minus B plus A. So we'll have O to B plus 1/2 to A minus B. We can expand out this bracket, so we've got B plus 1/2 of A minus 1/2 of B. We'll collect these B terms together, so we'll have 1/2 of A plus 1/2 of B. And this is the vector O to N. Now I could factorize this if I want to. For part B, show that M to N is parallel to O to A. So we'll have M to N and O to A. If we work out the vector M to N, this will be M to B plus B to N. And we know B to N is 1/2 of B to A. So M to B is 1/2 of B. And B to A, we know is A minus B. So we'll expand out the bracket and we'll collect the like terms. So we'll have 1/2 of A. This positive 1/2 will cancel with this negative 1/2. So M to N will just be 1/2 of A. Now we need to describe how this shows that M to N is parallel to O to A. Well, M to N is equal to 1/2 of O to A. We've got 1/2 A for M to N and 1A for O to A. So we can say, therefore, M to N is parallel to O to A. So whenever you have one vector that is a fraction or a multiple of another vector, they will always be parallel. They might not have the same magnitude, but their directions will be the same. And we call this 1/2 a scalar because it scales the vector O to A. Let's try example 2. So now we've been given the vector O to A is -3, 7, and 2, and we're given a vector for A to B. We need to work out the coordinates of point B. So the best way to do this is to sketch a diagram. And we need a fixed point. This is the origin. And from the origin, we go to A. This is our position vector. And I'll label this as -3, 7, and 2. This means the coordinates of A will be -3, 7, and 2. And from A, we go to B. And this is a direction vector. We have 4 in the I direction, -6 in the J direction, and 2 in the K direction. What we need to work out is the position vector from O to B. If I just move this up a little bit. Well, to work out O to B, we need to start at the origin and then go to point A. So this will be O to A. And then from point A, we need to go to point B. So we'll add the direction vector A to B. And we can add these two together using column vectors. So we've got O to A plus a to b. We'll add the I components and we'll get 1. We'll add the j components, another 1, and we'll add the k components and we'll get 4. So coming from the origin, we have points 1, 1, and 4. So these will be the coordinates of point B. Now we need to find the area of this triangle. So I'm going to sketch this out again, but as a triangle. To find this area, we can use the standard formula, a half AB sine C. The problem is we don't have the angle C. So we need to use the cosine rule to work out the angle, and I'm going to work out the angle at the origin. To work out this angle, we need the magnitude of each of these lengths. So we need to Pythagorize each of these position vectors. So for O to A, we'll have a square root of 9 plus 49 plus 4. We'll get root 62. For O to B, we'll have a square root of 1 plus a 1 plus the 16. We'll have 3 root 2. And for A to B, 16 plus a 36 plus a 4. And we'll get 2 root 14. So using the cosine rule, the cosine of theta will be the root 62 squared plus the 3 root 2 squared minus the 2 root 14 squared all over 2 lots of root 62 times 3 root 2. So when we work this out, we get theta would be the arc cos of 2 root 31 over 31, which gives us 68.9 degrees. So now we have the angle and we've got the lengths. We can use the area. So we'll have 1/2 of root 62 times 3 root 2 times the sine of 68.9. And this comes out as approximately 15.6 units squared. So we quite often have to apply trigonometric formulae when we're solving geometry problems with vectors. Let's try one more question. So in example 3, we've been given the points A, B, and C as 3 position vectors. We need to prove that ABC is a right-angled triangle. So do you want to give this question a go yourself? Think about which theorem applies for right-angled triangles. You can pause the video and come back when you're ready. Okay, so welcome back if you had a go. So I'm going to sketch 3 points that form something like a right-angled triangle. I'll call this point A, B, and C. Now we might not actually have the right angle at B, but this does give us a starting point. We need to work out the vector A to B, we need B to C, and we need A to C. Now the right angle might be at A or it might be at C, and if it turns out like that, I'll change my diagram. We also have a fixed point, which is the origin. We'll work out A to B. This will be A to O plus O to B. We can write this more simply as O to B minus O to A. Using column vector form, we've got 2, -3 and 3, minus O to A, 3, 4, and -2. So A to B, for the I components, we'll have -1, for the J, we'll have -7, and for the K, we'll have +5. Now, if this triangle is a right-angled triangle, we can apply Pythagoras' theorem. So I need to work out this magnitude. This will be the square root of the 1 squared plus the 49 plus the 25. This is 5 root 3. For B to C, this will be B to O plus O to C, or O to C minus O to B. Using column vectors, 4, -4, and 2, minus O to B, So we get 2, -1, and -1. So this will have a magnitude of 4 plus 2, which is √6. And then for A to C, we'll go from A to O, and we'll add O to C. So 4, -4 and 2, minus 3, 4, and -2. So A to C is 1, -8, and 4. Its magnitude, the square root of 1 plus for 64, plus for 16, and we get a magnitude of 9. So if our right angle is at B, then 5√3 squared plus the √6 squared will equal the 9 squared. So 5√3, and you can see the left-hand side does indeed equal 81. So our written statement then will be triangle ABC is right-angled at B as proven by Pythagoras' theorem. Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, you can download the worksheet and view the online lesson from my website, mrmathematics.com. I'll leave a link in the description below.